In this lesson, we're going to finish our conversation about basis, and then we're also going to introduce the idea of eigenvalues and eigenvectors. So first off, when it comes to basis, we've discussed the idea of the standard basis, which we denote with an E for some reason, I don't know. And then we have the non-standard basis. So today we're going to talk about what if we had two different non-standard bases and we want to convert from one to the other. That's what we're talking about here. So, and the reason we would want to do that is because some problems are easier to work in one basis versus the other. So we're going to talk about how to switch from one to the other. So consider this situation. So B represents one basis for a vector space that's made up of these two vectors, B1, B2. C represents another basis for the same vector space. And we're told that B1 is 4C1 plus C2, B2 is negative 6C1 plus C2. Now, keep in mind, again, these are both bases for the same vector space. So if I told you that C is a basis, that means that every vector in the space can be written as a linear combination of C1 and C2. Well, B1 is a vector in that space, so B1 can be written as this linear combination. And then we can say the same thing for B2. So it makes sense that B1 and B2 can be expressed as a linear combination of the C's because the C's form a basis. So we're told that the B coordinates for X are 3, 1, and we want to find the C coordinates for X. Okay. So keep in mind, if I told you this, that the B coordinates of X are 3, 1, that tells me that X can be written as 3 times B1 plus 1 times B2. And that's what the B coordinates mean. It means the weights or the coefficients in front of the B1, B2. Well, now I want to express X instead as a linear combination of C1 and C2. Well, there are different ways to go about it, but one option is just to replace B1 with 4C1 plus C2 and replace B2 with negative 6C1 plus C2. If I simplify that, I get 12C1 minus 6C1, which is 6C1, and then 3C2 plus 1C2 would be 4C2. So this tells me that the the C coordinates of X would be 6, 4. So another way to think about it would be this. Well, I guess just the observation I want to make here is that the X coordinates of, or the C coordinates of X, I should say, was equal to the product of a matrix and X. And that matrix actually is this matrix. Basically, create the matrix where it's the C coordinates of B1 and the C coordinates of B2. So that matrix would be, so the C coordinates of B1 would be 4, 1. The C coordinates of B2 would be negative 6, 1. And then we're going to take that and we're going to multiply that by the X, which was 3, 1. You'll notice if I did that, I'm going to get 12 minus 6 is 6. 3 plus 1 is 4. I'm getting the same answer. I think it's a more indirect, I don't know about indirect, but it's not as obvious a way to go. I think that just a straight substitution makes a lot of sense here. But it is worth just making that observation that if I just took the coordinates of B1 and the coordinates of B2, made those into a matrix, multiplying by that matrix had the same effect. So we can use that to come up with a way of converting from one basis to another. So first of all, this notation here, this is the change of basis matrix that changes from B to C. And notice that the columns, this column is the C coordinates of B1, C coordinates of B2, and so on up to Bn. This is called the change of coordinates matrix from B to C. So again, it allows us to take the B coordinates of some, if I took this matrix and I multiplied it by then, oh, you know what? I do have one correction I need to make here. I didn't multiply this by x, did I? Because I didn't know x. I'm actually multiplying it by the B coordinates of x. So if I form this matrix, which basically tells us how to change the B's to C's, this will then change the B coordinates of x into the C coordinates of x. There we go. So this matrix is made up of, let me summarize here again. This matrix, each column is how to convert the B's into C's. And then if I then multiply that by the B coordinates of x, the result will give me the C coordinates of x. There we go. Okay. Okay, so if we want to change, if we want to go the other direction, we want to go from C to B, then we would just use the inverse matrix. And we've discussed how to find the inverse matrix. Okay. Now, it's worth making an observation here. Previous sections, we said that to change to the standard basis, we multiplied by this matrix. Each column was basically the new basis. Another way to think about it is this is a way of changing from B to the standard basis, using the other notation here, because B1 is just the coordinates of B1 in the standard basis. Basis. Okay. So let's consider this situation. So we've got two different bases, B and C. So B is made up of these two vectors, C is made up of these two vectors. We want to find a change of coordinates matrix from B to C. Now, what I want to observe here is in the last example we did, we had a way of expressing B1. So it was basically something C1 plus something C2. And then we had the same was true for B2. We need to do the same thing here. We basically have to figure out what times C1 plus what times C2 is equal to B1. And then we'll do that for B2 in just a second as well. Please notice that that is the same as taking the matrix with the C's, so that'd be 1, -4, 3, -5, times x equals B1, which is -9, 1. So what I need to do now is basically solve this equation. This is then going to give me, I'm not comfortable using those x's, but basically this right here is going to be the C coordinates of B1. That right there is going to be the coefficients for C1 and C2 that will give me B1. So it's going to be the way of describing B1 in terms of the basis C. So let's solve this equation here real quick. So we've got 1, 3, -9, -4, -5, 1. 1, 3, negative 9. Okay, multiply the top row by 4 and add the bottom row. Gives me 0, 7, negative 36, negative 35. So 1, 3, negative 9, 0, 1, negative 5. And then finally I get 1, 0, 6, 0, 1, negative 5. Okay, so this tells me that the C coordinates of B1 are 6, negative 5. Let's do that again for B2. So I've got, it's basically the same augmented matrix we had before, but now we're using B2, so negative 5, negative 1. And so we get 1, 3, negative 5, 0, 7, multiply top by 4 and add the bottom, negative 21. Getting 1, 3, negative 5, 0, 1, negative 3. And then multiply the bottom by negative 3 and add the top. Is 4, 0, 1, negative 3. Okay, so the C coordinate of B2 would be 4, negative 3. So finally, my matrix that changes from B to C, and by the way, I have absolutely no idea why they do this arrows backwards. I don't have any clue. Sorry. So the change in basis from B to C, the first column would be the coordinates of B1 with regards to C, and the next would be the coordinates of B2 with regards to C, so that'd be 4, negative 3. Okay, so there's our change in basis matrix. Cool. There is a kind of a way of doing this all in one shot, and that is basically create these augmented matrices. So find the matrix of B and the matrix of, or the change of basis matrix for B, where we're changing to the standard basis, and then do the same for C. And then if we then reduce it so that the left side is the identity, the right side ends up being our the change that we're looking for. Okay, so let's find the change of basis matrix from C to B, and then the one going the other direction also. So I'm going to put, now please keep in mind, this is P sub B. Remember, it's not actually all that complicated. It's just each of these columns will be the B's. So this would be 1, negative 3. This would be negative 2, 4. Okay, and we're going to augment that with, and then P sub C are the vectors in C, so negative 7, 9, negative 5, 7. And now we're going to just reduce this until the left side is the identity. So we get 1, negative 2, negative 7, negative 5. Multiply the top by 3 and add the bottom. Gives me negative 2. Multiply by 3, so negative 21 plus 9 is negative 12. Multiply the top by 3 and add the bottom. So negative 15 plus 7 is negative 8. Yeah. Let me divide the bottom row by negative 2. We get 0, 1, 6, 4. And finally, let's see, the bottom row is good. And if I multiply the bottom by 2 and add the top, we get 1, 0, 5, 3. Okay, so the change of basis from C to B is the matrix 5, 3, 6, 4. Now we also need to find the change of basis from B to C. Oops, that should be P. change a basis matrix from B to C. But again, the nice thing is it's just the inverse of this one. That's a P. Sure, why not? It's just the inverse of this one. So remember, it's a 2 by 2 matrix. So 1 over the determinant. Remember, the determinant is 5 times 4 minus 6 times 3. So 20 minus 18 is 2. Times the new matrix where we switch the two entries in the main diagonal. That's the 5 and the 4. Switch spots. And then do the opposite of the other two spots. And so without having to go through all the row reductions, we've now got the other matrix as well. Okay, so great. So we started off needing to express the basis or finding the coordinates of the elements of one basis in terms of the other, right? That's where we started. But now if I just give you the two bases, just the vectors in the two bases, we can find the change of basis matrix without having to worry about going through and connecting one to the other. All we need to know is the two bases. Okay, cool. So next up, we're going to change directions completely. And now we're going to talk about something called eigenvalues and eigenvectors. And we're going to use the prefix eigen quite a bit. Just to give you a heads up, eigen just sort of means characteristic. So another way to say this would be, and I think it's German or something. I looked it up once, I don't remember. But basically the eigenvalues are the characteristic values, and the eigenvectors are the characteristic equations. But it's so much more fun to say eigen, so I'm just going to keep doing that. Okay, so here's what we're looking at. Let A be a square matrix. Okay, so in this section, we're only dealing with square matrices. Fine. This is the Greek letter lambda. I'm going to draw it by putting a little right side here and then a little leg on there. So that's lambda. The number lambda is an eigenvalue of A if there is a non-zero vector x such that multiplying the matrix A times x is the same as multiplying that scalar lambda by x. So basically, an eigenvalue, honestly, the vector is almost more interesting because multiplying the matrix by the vector is the same as just taking a scalar multiple of the vector itself. And that vector, we call that vector an eigenvector. So lambda is an eigenvalue, x is an eigenvector, and it's the eigenvector corresponding to lambda. So eigenvalues and eigenvectors are connected to each other. They correspond to each other. Anyway, so let's show that this vector, let's show that this vector is an eigenvector, and let's, that's it. Let's just do that. So to show that, we're going to do A times x. So A is this matrix, 0, negative 1, negative 3, 2, 3, 3, negative 2, 1, 1. We're going to multiply that by x. And so on the top, I'm going to get 0 plus 1 minus 3, so negative 2. And then we get 2 minus 3 plus 3 is 2. And then negative 2 minus 1 plus 1 is negative 2. Okay, so multiplying A times x, I got this result. Now, the thing that I want to notice is that this is the same as negative 2 times the vector 1, negative 1, 1. In other words, this is the same as negative 2 times the vector x. So multiplying A times x was the same as negative 2 times x. That tells me two things. First of all, that tells me that it's an eigenvector. And second of all, it tells me that the eigenvalue that corresponds to it is negative 2. Okay. So this is what it means to be an eigenvector. Showing that we have an eigenvalue, lambda equals 7, is definitely a little bit more involved. So let's talk about that. I'm sorry, there's a little typo here. This should say eigenvalue. So we want to show that lambda equals 7 is an eigenvalue. Okay, so to answer this question, really what I'm trying to show is that a times x equals 7 times x. And I don't know what x is. We'll figure that out in a minute. But this is what I'm looking at. If I were, let me do a couple things here. I'm going to subtract the 7x from both sides. So a times x a times x minus 7 times x equals. Now let's think about it for a second. A times x is a vector, 7 times x is a vector. So this will be equal to the 0 vector. Right? That's just the number 0. Next thing I'd like to do is factor out that x. Both terms have an x. I'm going to factor out an x. Now there are two things we need to observe. First thing I need to observe is if I factor out the x that I'm pulling out goes on the right side. Remember, multiplying by matrices and vectors, the order absolutely does matter. So that x is going to go on the right side. But the other thing is I can't just write a minus 7. It doesn't make any sense. A is a matrix. You can't just take a matrix minus a number. It doesn't make any sense. So the way I'm going to write it instead is a minus 7 times I. So when I say show that lambda equals 7 is an eigenvalue, what I'm really saying is show that this exists. And not only that it exists, remember, it has to be non-zero. Eigenvectors have to be non-zero. Lambda is an eigenvalue if there exists some non-zero vector x such that this is the case. So now what I'm left with doing is solving this homogeneous equation and showing that the result is more than just the 0 vector. So let's figure it out. Now let's remember that a minus 7i, so a was 1652, minus 7 times I would be just 1001. If I bring in that 7, this becomes 7007. And if I subtract this, notice that when I subtract it, only the main diagonals change. So this becomes negative 6, 6, and this will be 5, negative 5. Only the main diagonals change. So basically, subtracting the 7i is the same as subtracting 7 from just the main diagonal. So this equation is the same as solving the equation negative 6, 6, 5, negative 5, augmented with the 0, 0. And certainly if I divide the top by, negative 6, and the bottom multiply and subtract. Anyway, both rows are multiples of each other, so this would be 0, 0, 0. The thing to observe is that x1 is equal to x2. In other words, x is equal to the vector 1, 1 times some parameter, and I'll just call it t. And I think this is getting more into what we're trying to prove. Basically, at this point right here, I've proven that 7 is an eigenvalue because this equation has more than just the trivial solution. It's got an infinite number of solutions, but certainly it's more than just the 0 solution there. So 7 is an eigenvalue. Now, when we solve this equation, a minus lambda I equals 0. Sorry, that's a typo also. This should be a minus lambda I times x equals 0. That's what we were solving there. We solved this homogeneous equation, and what I want to point out is basically what we found was the null space of the matrix a minus lambda I. Because, remember, the null space describes all solutions of the homogeneous equation, and that's what we did. We found the, and in fact, we went a little further. We showed that null space, so it was the null space of not a, but a minus 7i, was the span of that one vector, which in this case was 1, 1. So we proved that. So the solution to this equation gave us the null space of A minus lambda I. This is a subspace. We're going to call that the eigenspace because, again, in this chapter, kind of everything starts with the prefix eigen. It's the eigenspace of A corresponding to that eigenvalue lambda. And so let's find, so we're told here in this example that lambda is an eigenvalue, lambda equals 2, and we want to find a basis for the corresponding eigenspace. Okay, so I don't need to go through the whole process again. I know what I'm doing here. We're going to be considering the equation A minus lambda I. I'm sorry, not, well, let me clear all that out. A minus 2i, right? We're told lambda. A minus 2i times x equals 0. We also discussed subtracting 2i basically means subtract 2 from just the main diagonal. So that means that we're going to get 2, negative 1, 6, 2, negative 1, 6, 2, negative 1, 6. I think I see a pattern here. And 0, 0, 0. And certainly this is equal to, the second and third rows don't matter. So we get 2, negative 1, 0, 6. And so this tells me that 2x1 minus x2 plus 6x3 equals 0. And so now I should mention here real quick, I'm going to solve for x1. You don't have to. You can solve for any one you want. It really doesn't matter. It's pretty easy to solve for x2 actually here, but just out of habit, I'm going to solve for x1. x1 is equal to 1 half x2 minus 3x3. And so my solution here, so 1 half x2 minus 3x3, and then just x2 and just x3. And so this is equal to 1 half 1, 0 times x2, and then negative 3, 0, 1 times x3. And so the basis that I'm looking for here is those two vectors. 1 half 1, 0 and negative 3, 0, 1. And by the way, if you don't like that fraction, you can just take that whole matrix and multiply it by 2, and using that instead of the one that I wrote still will give you a good basis. So there's nothing wrong with scaling that vector up. It won't mess you up at all. Okay. Some observations here. If we have a bunch of eigenvectors that correspond to distinct eigenvalues. So let me back up for a second. If we have a bunch of distinct eigenvalues and each one of them has an eigenvector. Okay, so v1, v2, v through vr all correspond to distinct eigenvectors. I mention that because, and I don't think we're going to get into it in this class, but one eigenvalue could correspond to more than one eigenvector. And I really don't want to get into it any more than that, but basically we're just assuming that v1, v2 up through vr are correspond to distinct eigenvalues. The observation here is that the set of those vectors is linearly independent, and we're going to come back to that a little bit later. Okay. Let's show that this vector, or this value, that lambda equals 3 is an eigenvalue of this matrix. So again, and we saw an example of this earlier. We are going to consider A minus, in this case it's A minus 3i times x equals 0, and we want to show that this is has a non-trivial solution, and we're bleeding somewhere. I'm not just doing the same problem again. So we get, subtract 3 from the main diagonal, so I get 0, 6, negative 8, 0, negative 3, 6, and 0, 0, negative 1. Oh, I'm sorry, I meant to augment that. Oh, where'd you go? Here you go. Okay, augment that was 0, 0, 0. And let me switch the second and third rows, or the first and second rows, I should say. So 0, negative 3, 6, 0, 0, 6, negative 8, 0, 0, 0, negative 1, 0. I'm going to divide the top row by negative 3, so we get 0, 1, negative 2, 0. I'm going to switch the second and third, the second and third row, so we get 0, 0, and also multiply by negative 1. Let's see. Multiply the top row by negative 6 and add the bottom row. I'm getting 0, 0, 4, 0. I don't even know why I'm... Yeah, let's keep going. Okay. 0, 1, negative 2, 0. 0, 0, 1, 0. And then the bottom row is going to be all zeros. And then finally, I'm going to get 0, 1, 0, 0, 0, 0, 1, 0, and then the bottom row is all zeros. Okay, what did I learn? I learned that in this case, the top row tells me that x2 is 0. The second row tells me that x3 is 0. And that's all I've got. That's all the information I've got. So that tells me that my solution, the second component is 0 and the third component is 0. But the first component can be anything it wants to be. So this would be the vector 1, 0, 0 times x1. Right? The only restrictions are x2 and x3, but x1 can be anything it wants to be. Consider this. The first column does not have a pivot. So the first vector is my free variable. Or the first x1 is my free variable. Anyway, again, all I had to do was show that there was a non-trivial solution, and certainly we found that there was one here. The observation that I want to make from this example is that if we have a diagonal matrix, remember the diagonal matrix means that there's numbers along this diagonal, and they could be 0. In this case, there is one. There's numbers along this diagonal and nothing but zeros below it. Another example of a diagonal matrix would be kind of the flipped version of that, where we had like 3, 0, 2, and now there's all the zeros on the top, and then there's some numbers on the bottom, whatever, I'll just put question marks. That would also be an example of a diagonal matrix. Anyway, the eigenvalues of a diagonal matrix are the entries on the main diagonal. We could prove that. I don't think we're going to get into that, why that works, but we could show that it works. Please notice that in that last example, lambda equals 0 is also an eigenvalue because, again, on the main diagonal, 0 is one of them. In fact, just looking at that matrix real quick, that tells me that the eigenvalues are 3, 0, and 2. Because those are the 3 entries on that diagonal. When 0 is an eigenvalue, that means that a times x equals 0 times x, okay? Or, again, 0 times x is just 0. That means that ax has a non-trivial solution. One more time. An eigenvalue means that this equation has a non-trivial solution. Okay, now let's think about that for a second. if this has a non-trivial solution, that means that A is not invertible. Okay, we had that whole list of stuff. In fact, here's my list of stuff. The invertible matrix theorem. One of the things that it said was, if A is invertible, then this homogeneous equation has only the trivial solution. So, if this has a non-trivial solution, let me go back for a second. If this has a non-trivial solution, that means that lambda equals 0 is an eigenvalue. So if this has only the trivial solution, that means that the number 0 is not an eigenvalue. We can add this to the list. So, one more time. If A is invertible, 0 is not an eigenvalue. And I'm going to add one more thing to this list, and we actually saw this earlier. Maybe we just never got around to adding it. Another condition or another equivalent statement of an invertible matrix. A matrix is invertible if the determinant of the matrix is non-zero. And I don't think we're going to get into that about why that works too much, but we certainly saw that in earlier chapters when we found the determinant. Well, consider this. When we find the inverse of a matrix, one of the things we do is in front we put 1 over the determinant of the matrix. Well, if we do 1 over 0, that means that the inverse does not exist. So if the determinant is 0, then the inverse does not exist. Okay, so just a couple more things to add to our list. Okay, so for more complicated matrices A, so far we haven't really found the eigenvalues. All the examples we've had so far, I've either given you the eigenvector or I've given you the eigenvalue. If it's a diagonal matrix, I don't have to. If it's diagonal, we know what the eigenvalues are. Just look at the diagonal. But what if we wanted to, I said, here's a matrix, find the eigenvalues. Obviously, that's an important question to be able to answer. We're going to need a process. So what we're going to do is we're going to start with this equation. Now, here's the thing. If this equation has a non-zero solution, let's think about this. If this equation has a non-trivial solution, meaning that x, the eigenvalue vector, exists, by the invertible matrix theorem, that means this has a non-trivial solution only when this matrix is not invertible. Now again, I'm not talking about A. I'm talking about this other matrix, A minus lambda I. So this equation has a non-trivial solution only when A minus lambda I is not invertible. And if A minus lambda I is not invertible, that means that the determinant is 0. There's that last condition. Now, I'm basically saying the opposite of everything in the invertible matrix theorem. I'm saying this has a non-trivial solution, which means that this matrix is not invertible, which means the determinant is equal to 0. This equation here, the determinant of A minus lambda I equals 0, is called the characteristic equation of A. And that equation is going to end up being an equation with the variable lambda, and then we're going to solve that equation for lambda. So let's see that process in action. Let's find the eigenvalues of this matrix. So again, the first thing I'm going to do is find the determinant of A minus lambda I. This is the first example where we are not given lambda, we actually have to solve for it. So we're going to find the determinant of again, we're going to take the entries of A, and each of the entries in the main diagonal, we're going to subtract lambda. Right? In the earlier example, when we knew that lambda was 2, we just subtracted 2 from each of those. Well, here, I'm going to take that diagonal entry and subtract lambda. I'm going to take the other diagonal entry and subtract lambda. It's going to be a little weirder because now we don't have a number to subtract, we just have the variable. But it's the same idea. I'm going to find this determinant. So 2 minus lambda times negative 6 minus lambda minus 9. Let's clean this up. So we get lambda squared plus 6 minus 2, so plus 4 lambda minus 12 minus 9. So we get lambda squared plus 4 lambda minus 21. We can factor this as lambda plus 7 times lambda minus 3. And again, we know that the determinant of a minus lambda I is equal to 0. And so for that reason, lambda is negative 7 and lambda is 3. And so we have our two eigenvalues. And we can, we're not going to, but we could then check to make sure that this is actually true by the process that we saw in the earlier examples to verify that these are eigenvalues. Okay, let's try this problem. Let's find the eigenvalues and the bases for the corresponding eigenspaces for this. So one more time, we're going to find the determinant of a minus lambda I. One more time, we're going to subtract lambda from just the main diagonal. So 3 minus lambda, 0, 0, 0, 2 minus lambda, 2, and 0, 1, 1 minus lambda. Now the nice thing is all those zeros make this a pretty easy determinant to calculate. It's going to be 3 minus lambda times the smaller matrix, so it'd be 2 minus lambda, 2, 1, 1 minus lambda. So this is going to be 3 minus lambda. And then we've got, let's see, 2 minus lambda times 1 minus lambda minus 2. So we're going to get lambda squared minus 3 lambda plus 2, but then minus 2 is just nothing. If let me see, so this would be 3 minus lambda. I can pull out a lambda and I'm left with lambda minus 3. And then the last thing is I'm going to notice that I can take a negative out of the first parentheses. And so this becomes lambda minus 3 squared. And so my eigenvalues are 0 and 3. All right, let's now find the corresponding eigenvectors, or the bases for the eigenspaces. So let's start with lambda equals 0. Now let's remember I'm solving the equation a minus 0I times x equals 0. And so let's see, I'm going to solve this. So the a was, where'd it go, 3, 0, 0. I'm subtracting 0 from the main diagonal, which obviously changes nothing. Oh, shoot, I'm going to augment that. Okay, I'm going to divide the top row by 3. Divide the middle row by 2. And the bottom row is just going to disappear. And so I'm getting that x1 is 0. x2 is equal to negative x3. So the x1 is going to be 0. x2 is negative x3, and x3 is just itself, because x3 is my free variable. And so this is the matrix, or the vector is 0, negative 1, 1 times x3. So the basis I'm looking for here is made up of just one vector, and that would be the vector 0, negative 1, 1. Okay. The other eigenvalue we found was 3. So now I'm doing a minus 3i times x equals 0. So now I'm subtracting 3 from the main diagonal, gives me 0, 0, 0, 0. That's fairly boring. 0, negative 1, 2, 0. 0, 1, negative 2, 0. Okay, if I do a little bit of rearranging, the top row, I'm going to make that 0, 1, negative 2, 0. And then the others are all zeros. Okay, so this tells me that x2 is equal to 2x3. Okay, so in this case, I have two free variables. x1 can be whatever it wants to be. x2 we said was 2x3, and x3 is also free. So we're getting the vector 1, 0, 0 times x1 plus 0, 2, 1 times x3. And so this time my basis is made up of two vectors. The vector 1, 0, 0 and the vector 0, 2, 1. Okay. Now, we've got our answer here. The thing that I want to point out is finding this determinant is a bit of a pain. I mean, in this case, it wasn't a big deal because there were all those zeros, which made things really nice. But I just want to point out, solving in general, finding this determinant is a bit of a pain. And not only that, notice that what I ended up with was a cubic equation. Now again, in this example, it wasn't that big a deal to solve the cubic because the 2's canceled and there was already the 3 minus lambda factored out. And so it wasn't too difficult to solve this. But in general, finding the eigenvalues of a 3 by 3 matrix can be a bit challenging and require a bit of algebra. So we're going to look for some ways of simplifying things a bit. So let's take a step back and just remember some properties of determinants. So when A is an n by n matrix, by the way, 3 by 3 is bad enough. Imagine n by n. The characteristic equation is going to be an nth degree polynomial equation, which, yeah, not fun. So I've got it right there. Definitely harder to solve. And so to make life easier, let's remember some properties. These came up in previous chapters when we were talking about the determinants. So first off, let U be an echelon form of A, obtained by replacements and interchanges. So no scaling. So we can switch the rows however much we want. Remember, a replacement means replace a row by itself plus a multiple of another. So you can multiply, as long as the row is multiplied, as long as the row is as long as the row is replaced by itself plus a multiple of another row, the determinant does not change. So if we were to scale, meaning multiply or divide a row by a constant, then the determinant does change. Also, I want to remind you that switching two rows changes the sign of the determinant. So the determinant of A is basically the same as the determinant of U, except that we're going to multiply by negative 1 to the r, where r represents how many times we swap two rows. So again, each time we switch two rows, we multiply by a negative. We should point out also, if A is not invertible, the determinant is 0. We've already established that. So this is one thing that could be useful. Again, the whole point is, first you reduce A to echelon form, keeping track of what you did along the way. Some other properties of determinants that make life a little bit easier. The determinant of a product is the product of the determinants. That'll come in handy a little bit later. The determinant of A transpose is the same as itself, determinant of A. If A is triangular, then the determinant of A is the product of the entries on the main diagonal. It's interesting. I'm saying triangular, but I used the word diagonal earlier. I'll have to look into that. Anyway, triangular, diagonal, they both mean the same thing, where there's entries in the main diagonal. I shouldn't put zeros, I'm sorry, I'll just put boxes. Boxes in the main diagonal. And either zeros above and then zeros below and other things above, or again, could be vice versa. Those boxes that I put, the product of those is your determinant. Row replacement doesn't change the determinant. We just talked about that. Interchanging changes the sign, and scaling also scales the determinant by the same factor. So we've discussed all that. So just to remind us, let's find the determinant of this matrix. And again, let's do it by first taking this matrix and reducing it. So we've got the matrix 1, 5, 0, 2, 4, negative 1, 0, negative 2, 0. I'm going to start. So the top row is fine, bottom row is fine. I'm going to start by replacing row 2 with itself plus negative 2 times row 1. So we get 0. Negative 2 times row 1 is negative 6, negative 1. Okay. This this row operation does not change the determinant. So I'll just write no change. Okay. Next thing I'm going to do is I'm going to so top row is fine. I'm trying to think of what I want to do next. Do I want to switch them? So, okay. Why don't we leave the 0, negative 6, negative 1 where it is? Now I need to be really careful. If I want to turn this into a 0, I'm tempted to multiply the bottom row by negative 3. The problem is I can't replace row 3 with negative 3 times itself. I need to, and let me write it out here, I'm going to replace row 3 with row 3 minus 1/3 times row 2. And again, the important thing is row 3 is being replaced by just itself combined with a multiple of another row. That is acceptable. But again, by doing that, once again, the determinant will not change. There were other options I could have done. I could have swapped the second and third rows, and that's okay. But that would change the sign. Whatever, it's okay. It's just, yeah. So I'm getting 0, 0, and then negative 1, so this would become 1/3. And so now the determinant of A becomes the determinant of that reduced matrix. Oops. And that is equal to 1 times negative 6 times 1/3, which would be negative 2. Basically, if you're doing row reduction to try to calculate the determinant, you have to be real conscious of which changes you are making, because as you make changes, sometimes that does change the value of the determinant. Okay. Let's consider this problem here. Find the characteristic equation of this matrix. Now, we could go through and set up the whole thing, but what I want to observe here is I already know what my 3 eigenvalues are going to be. Because this is a diagonal matrix or triangular, I don't know. I'll have to go back and look and see if I'm using those words right. But if I'm using a diagonal, if it's a triangular matrix, the numbers on the diagonal are my eigenvalues, which means that the characteristic equation is just lambda minus 3 times lambda minus 1 times lambda minus 2 times lambda minus 3. That's it. That's my characteristic equation. Knowing what the eigenvalues are definitely makes it a lot easier to find the characteristic equation instead of vice versa. In this example, we're going to say that lambda equals 3 is an eigenvalue of multiplicity 2, again, because it appeared twice. And in fact, our earlier example was the same way. We had lambda minus 3 being a repeating factor, and so we say that it's an eigenvalue of multiplicity 2. Okay, we can go into a lot more depth about eigenvalues, but I'm just going to say that for this class, we're only going to be interested in real valued eigenvalues. Now, I say that because if we're solving a polynomial equation, there's always a possibility of getting complex solutions to that equation. We're not going to worry about that in this course, but just realize if you go into other courses that deal with eigenvalues, there is a possibility of getting complex eigenvalues, and that's okay. We're just not going to worry about it. Also in this class, when we solve characteristic equations, I'm only going to expect you to solve quadratics. I'm not going to expect you to do a higher degree polynomial equation. Yeah, I mean, there are methods you might have learned, you may remember learning in, I don't know, pre-calculus or algebra 2 or something, but we're not going to worry about it. All right, one more definition that we need to talk about that really, more than anything, leads into what we're doing in the next section, next few sections. We say the two matrices A and B are similar if A is equal to P times B times P inverse. We're not getting into what is P right now. We'll get to that, worry about that later. Basically, P is any matrix. And so A is equal to some matrix times B times some other, the inverse of that same matrix. So we say these two matrices are similar. And changing, and I'm sorry, this is a mistake. There should be an A here. So making that change from A to P inverse is called a similarity transformation. Again, transformation takes one matrix and turns it into a new one. Well, if it changes it into a new one that is similar to the original, then we say that it's a similarity transformation. That's it. Okay, one property for now anyway. If two matrices are similar, then they have the same characteristic equation. Okay. And so therefore they have the same eigenvalues with the same multiplicities. So let's prove it. So let's start off by talking about A minus lambda I. Now, let's make a couple of changes. By the way, I'm sorry, I should have started off with this. We're going to assume that A is equal to P, B, P inverse. And we want to show that A and B have the same eigenvalues. Okay, so that's what we want to show. So let's start with just this A minus lambda I. Now let me make a couple changes. Instead of A, I'm going to write P, B, P inverse. Oops. Minus lambda times. Instead of I, I'm going to write P times P inverse. Because, of course, P times P inverse is just the identity matrix. And so I'm rewriting it that way. Now, I'm going to take that, and I'm going to factor the P out of the left side. Now, keep in mind, this lambda is just a number. It is not a matrix. Because it's a scalar, we could move it around as much as we want. I could take that lambda and stick it in the middle there if I really wanted to, because it's just a scalar. So I'm going to factor a P out of the left side, excuse me. I'm going to factor a P inverse out of the right side. And then what I'm left with is B minus, well, again, just like before, I can't just say B minus lambda. It's minus lambda I. Now, when I take the determinant of A minus lambda I, this is equal to the determinant of P times B minus lambda I times P inverse. Right? Because we showed that this matrix is exactly equal to this matrix. This product, I should say. Now, we had that property earlier that said that if you have a product of matrices, the determinant is the product of the determinant. So this is equal to the determinant of P times the determinant of B minus lambda I times the determinant of P inverse. Okay, now I'm going to claim that the product of these two, by the way, keep in mind, a determinant is just a number. Now we can rearrange, right? These are just numbers. Oh, a number times a number. You can rearrange them. So I can take this determinant and just rearrange it so it multiplies directly with this one. And I claim that that product is just 1. And I'll show you why that's true in just a second. So hopefully you will agree that P times P inverse is equal to the identity matrix. Well, that means that the determinant of P inverse is equal to the determinant of the identity matrix. Well, on the left side, this is the same as the determinant of P times the determinant of P inverse. And the determinant of the identity matrix is just 1. Remember, the identity matrix has 1s on the diagonal. Well, the determinant is the product of those 1s, which is just 1. And so the determinant of P times the determinant of P inverse is just 1. And so we're left with this determinant equals this determinant. And those two determinants, the one on the left is the characteristic equation for A. The one on the right is the characteristic equation for B. And if they're equal to each other, then they have the same characteristic equation, which means that they have the same eigenvalues. So check. Okay, we proved it. Awesome. So as I said, this whole idea of similar matrices is going to be pretty central to what we're going to be doing next class. But that brings us to the end of this lesson. Thank you very much, guys, for watching.